Ladies and gentlemen, the topic of my presentation is challenges in recycling, upcycling of solid hazardous waste for using in construction. I'm representing the National Building Research Institute, which is a joint venture of the Technion as a leading polytechnical university in the country and Ministry of Construction and Housing of Israel. Here's the outline of my presentation, including motivation, explanation about chemical and radioactive contaminants in industrial residues, norm. I will describe what does it mean norm later on. And I will give you some examples of interdisciplinary technologies developed in the Technion to purify contaminated industrial residues for their safe and cost-effective use in construction industry. And I will finish with a philosophical question, how to proceed in the future. Motivation. Let's start with the pollution and degradation of the environment. We know well that construction doesn't only consume about 40% of materials produced in the world and about 1/3 of industrial energy, but also pollutes. Extraction of minerals results in noise, vibrations, air pollution, transformation of land. Don't forget, consumption versus end products. Yes, we consume huge quantities of exhaustible or non-renewable resources, we know it. Industrial production increased for the last century more than by 50 times. And most of this growth happened in the second half of the previous century. Unfortunately, only 5% of natural resources turns to end products. And the rest goes simply to a waste, often ecologically harmful and unsafe. I will discuss in my presentation why recycling is not so easy and what are the pros and cons. Coming back to the disposal of the large amount of solid byproducts. It has become a serious environmental problem. Landfilling is a problematic. It's a practice which is under examination for environmental concerns. And land disposal poses long-term potential environmental risks. Our opinion is simple. This waste should more likely be regarded as resources placed in the wrong place. So considerable research is being conducted worldwide on the reuse of waste materials in order to deal with the increasing threat of the release of toxic elements. And economically viable solutions should include, of course, the waste utilization for new products rather than land disposal. The best way, of course, to handle this toxic industrial waste is to avoid generating them. Of course, government, like we suppose, should promote and support educational and training programs and establish policies that encourage waste minimization, reuse, recovery, recycling, and also regulation and monitoring of collection, transportation, treatment, and disposal of toxic industrial waste are simply crucial. Let me speak in more detail about chemical and radioactive pollutants. I will focus on radioactive because very often it's much more easier to get rid of chemical pollutants than radioactive. Norm. Norm has a double meaning. Norm is a norm, normative, and norm is abbreviation of naturally occurring radioactive materials. Natural radionuclides derived from rock and soil, and many mineral materials are extracted from the earth, from the rock and soil, and used in construction. I'm not speaking about polymer, wood, and metals. About mineral materials, I'm speaking mainly. In the uranium series, the most important and most popular reference is radium. So this disintegration chain of uranium is often called radium chain. The worldwide average concentration of radium, thorium, and potassium in the Earth crust is 40, 40, and 400 becquerel per kilogram. And building materials are considered as gamma emitters because they contain all of them in different proportions, of course. And some of them, mainly in the zones close to Chernobyl disaster in Belarus, Finland, the regulation addresses the cesium-137 concentrations on also. So we are speaking about natural origin and industrial byproducts materials. And the task of the regulators is to limit the use of materials that cause a significant increase in gamma and also in the radon. Because radon, we can breathe it. It's in the middle of the disintegration chain of uranium, and it's only a gas. The rest of the chain of uranium, disintegration chain, is metals, aerosols. Enhanced radioactivity is observed in many different types of byproducts, because after some chemical or thermal treatment, the concentration of anorganic matter, including heavy metals and including radioactive metals like radium and thorium, is increased. Among them, slag, different kinds of ash, phosphogypsum, and red mud. Recently finished project I took apart called Norm for Building addressed different kinds of industrial products contaminated with norm. We published a book, I think it's a good book, very popular now, which is called Norm for Building. So I recommend to the listeners to read this book. Please look at the table taken from one of the European documents, RP 112, and look at the bottom of the table, listing 3 types of industrial byproducts: phosphogypsum, blast furnace slag, and coal ash. They contain much, much higher concentrations of radionuclides than most common building materials in the upper part of the table. Disposal of these solid hazardous byproducts can lead to the severe environmental damage, like what happened in Hungary in 2010, the worst ever ecological disaster, when a huge territory of Hungary was simply flooded by this toxic byproduct. Red mud is a high alkaline residue of bauxite industry. And look at the numbers. Only in China, the amount of red mud discarded is estimated to be more than 30 megaton per year. It's not only in China and Hungary. It's also in many other countries. In Australia, in the United States. We dealt with one of the sources. The sample was sent to us from Texas, and you can see it has elevated concentration of radium and thorium. Blast furnace slag sometimes also has contamination, radium. And finally, phosphogypsum, which is a very painful problem for all mankind, because the fertilizers should be produced more and more every year. And phosphorus is a very important, vital element for agriculture, together with potassium and nitrogen. Phosphogypsum, unfortunately, contains chemical and radioactive impurities. Chemical are injurious to the setting time, strength of some building binders, result in efflorescence, corrosion of steel. And radioactive impurities are coming from radium, mainly radium, which is elevated. Look at the quantities. Like in red mud, we are speaking about enormous amounts, billions of tons. Stacks are growing in 52 countries. And these stacks are often located in highly sensitive populated areas, like in central Florida, in south of Spain and Sevilla. Look at this photo. More than 100 million tons are disposed there. Tunisia, look at the populated area nearby. Florida, about 2 billion tons of this contaminated product is landfill. Florida, Belarus, South Korea, look at this long pipeline pumping the slurry of phosphogypsum from the powerful phosphate plant to the disposal site. This is our photo, which was made 20 years ago when I was a little bit younger. Current solutions existing in the literature are based on separation by grain size, but you can compare the phosphogypsum and different fractions. So there is no big difference. This is not radical solution to separate the fractions. It does help too much. Other solutions, many of them, are based on phase changes, moving from one type of hydrate to another. Dehydrate, hemihydrate, dehydrate of calcium sulfate. But unfortunately, like we understood, it can purify from phosphates and maybe from some other chemical contaminants, but not from radionuclides, because radium sulfate, which is responsible for radioactivity, crystallizes there first and cannot be simply washed out from the surface of the crystals. Our proposed research is based on chloride complexation with radium to prevent precipitation of radium salts. By the way, high chloride concentration is in the agent, which is in our case calcium chloride, but it's in recycle, so we don't consume too much this agent. This is very cheap agent, by the way. You can compare the solubility of chloride and sulfate of radium, several orders of magnitude. So the task is how to move from insoluble, practically insoluble radium sulfate to soluble radium chloride, and then how to filter it, how to get rid of this radioactivity. And it was done by a complex treatment based on thermal, but not under high temperatures. Look at the temperature on the right side of the slide, and phase changes, and also agitation. It means a complex mechanochemical treatment. It's a part of our patent. So we studied the effect of chloride concentration. We studied the effect of temperature. We understood well what is the optimum parameters, what is the effect of calcium chloride, what is the optimal concentration of calcium chloride in solution. And then we proposed for the industry, for one of the plants, this scheme of producing environmentally safe and cost-effective products for construction. Now let's ask ourselves, what are these contaminants? They are contaminants or valuable elements. When we recover these contaminants, we call them contaminants in the construction. But for other industries, they consider them as a very valuable elements. Rare earths, radionuclides, radium-223, very valuable for radiopharma, phosphates, fluorides. Applications of purified calcium sulfate hydrides are many. Dehydrate, hemihydrate, anhydrate, binders. One of the important issues, what to do with the disposal of removed contaminants, because the concentrations are getting high. And then we need to dispose them. So we used in our research different approaches. Fine fraction of gypsum can be useful. Of course, some gypsum is lost. Zeolites, both natural and artificial, good. Geopolymers. A little bit about coal fly ash, which is a very popular product, byproduct, but considered as a resource mainly in construction. We know it. Coal fly ash production in several countries, like in China, in Poland, is still increasing. We have so many nice examples of using coal fly ash in concrete industry, ready-mix, precast, on-site applications. But when used as the main component of building materials, it may result in enhanced exposure to gamma. And Israel Ministry of Environmental Protection, which is our regulator, announced coal fly ash in 2008 as radioactive waste. Of course, this is not waste. It's against all the international laws and norms, European, international, and even national. And then you can imagine what was in the local construction industry. All the industry was in deep shock after years and many efforts of educating the industry, how to use, how to promote different recycling solutions for coal fly ash. And we studied in depth the effect of natural radiation. We compared different materials, concrete, containing and not containing fly ash. We came to the conclusion that the total dose or radiation dose from both gamma and radon is almost the same, because radon emanation is much lower. It's very difficult for radon atoms to escape very dense, glassy structure of the fly ash particles formed under high temperatures in the thermal plant. The next question we asked ourselves, is it worth to purify fly ash from norm? And in the meantime, the answer is not. We are not in this stage. And another research we've done was, can we utilize fly ash for adsorption of radioactive and other contaminants from contaminated wastewaters and soil? And not only fly ash, by the way, red mud. But for this purpose, we need to produce somehow the zeolites. So we have to move from amorphous structure of fly ash to the crystalline structure of zeolites. Zeolites, just to remind you, large group of microporous crystalline aluminosilicates made of 3D framework, like you see in this slide. This structure is unique. Please look at the radius of atom. So it can be effectively used for adsorbing contaminants, different kinds of ions, heavy metals, including radium and thorium. Why not? Many projects running in the world of producing artificial zeolites from coal fly ash, they use different technologies. Our technology is a little bit different. This is the material we used in our experiments, a composition of our fly ash. And we successfully produced artificial synthetic zeolite, which was very close to the natural one. It is helpful to adsorb ammonium ions, adsorb lithium, and please look at the temperature. Temperature low, relatively low. What does it mean, 175? It's not very high temperature. So consumption of energy is minimum. And by the way, our technology is continuous in contrast to the batch-based technologies used in other labs. And one more example, valuable admixtures like corrosion inhibitors made of very toxic silicofluoric acid, the byproduct of the phosphate fertilizers. This is the result of the last project we've done in the Institute with using one of the salts of silicofluoric acid, potassium salt, in comparison with other known corrosion inhibitors, organic MCI and unorganic CNCI inhibitors. And look at the total corrosion. It's minimum in this corrosion inhibitor. And then I would like to finish my presentation with a question, what to do in the future, how to proceed. And the answer is simple, but it's very difficult to get it. We need, first of all, to establish a common language and cooperate between these three blocks in this triangle diagram. Consumer, we are all consumers, by the way. Government, which is responsible for the environmental protection, and producer. Yes, we need to take care of the interest of the producer. Thank you very much from the city of Haifa.